Assalamualaikum. Hi, my name is Putri Alamelina binti Ibrahim. My matrix number is 8180110 and my supervisor is Dr. Azwan bin Safid. Welcome to my presentation video. So today I'm going to present my final year project entitled Aerodynamic Study of Formula One Car Performance in Wake Flow using Computational Fluid Dynamics. So we'll begin with the introduction. Why do Formula One aerodynamics matters? Aerodynamics are fundamental in the entire design of an F1 vehicle. The primary purpose of an aerodynamics is to produce downforce and reduce the drag. The front wing works in the opposite way of how an aircraft wing works. The airflow lowers the pressure underneath the wing, with the pressure imbalance generating downforce, and this is what keeps the car from taking off. Higher downforce means the car is pushed harder into the track, giving tires more grip, and that means shorter braking distance, harder acceleration, and higher cornering speed. Downforce also ensures the performance and the safety of the driver. Higher downforce means less sliding, which prevents oversteer and reducing tire wear. So it also helps with reduce the fuel consumption and the emission level. Next, what is this wake flow or dirty air? Well, how does it form? So when air flows over the surface of an F1 car, it creates a wake of a turbulent air or dirty air that hinders the aerodynamic flow of the car directly behind it. The airflow from the front and underneath the car merge with the rear wing and it produces an upwash, substantially impacts the wake characteristic. Dirty air reduces the efficiency of the following car's aerodynamic surfaces. It lowers the downforce, slowing it in corners and reducing the effectiveness of the car's cooling system. According to F1, current F1 cars loses about 35 to 47% of their downforce when they are around 3 car lengths behind another car. But the new 2022 rule promised to lessen those downforce losses about 4 to 18%. Next, the problem statement. What issues that inspired this project? For many seasons, racing fanatics has publicly deemed that F1 has lost much of its thrilling aspect due to the difficulties of the car trailing each other closely for an extended time due to the turbulent wake generation and the stroke flow generated by the leading car. Second, there are not many full publicly available studies regarding the influence of wake flows on a full Formula One car. So part of the aim of this study is to assist narrowing a research gap on the effect of wake flows on F1 car. Next, what needs to be achieved in this project? What are the objectives? So the first one is I want to conduct an aerodynamic simulation of the 2 car models using ANSYS Fluent. Second is to analyze the wake formation around F1 car models using free stream conditions and wake flows. And finally is to evaluate and compare the values of downforce coefficient, drag coefficient, and front balance with the distance between 2 F1 cars. Moving on to the next part, the literature review. So what has been done previously? This is a graph plot that compares the average Formula One downforce and lift-to-drag ratio. In Formula One, an aerodynamicist is primarily concerned with the generation of downforce to reduce the lap time. If we take a look at the graph, downforce greater than 3 times the car weight is possible depending on the car configuration and the regulations enforced. Formula One cars have several important aerodynamic areas: front wing, rear wings, dashboard area, sideboard area, floor, diffuser, and many more. Every component of each of these areas contributes to the performance and the efficiency of the car. The numerical prediction studies often deal with some common aerodynamic parameters: downforce, drag, overall aerodynamic efficiency, the front balance, which also will be considered in the study as well. Next is the previous research study for 2017 F1 cars under the wake flow by Guerrero and Castilla. If you take a look at the image on the right, it can be seen that the second car is affected by the flow that is lower in terms of kinetic energy as the weight that is generated by the leading car is released far away, disturbing its follower. As the second car gets closer, it inherently enters into a mushroom-shaped wake structure characterized by a very low speed flow that ranges from 0 to 10 meters per second, thus resulting in its downforce being severely affected. So at a large distance, about 2 lengths, if you see at the most bottom image, the second car wake adopts a needle shape which somehow imitates the free stream natural wake. So we can expect our simulation to be almost but not quite similar to that. Next, so this is the model comparison between the 2021 and 2022 F1 cars. There are drastic changes mainly involving these 2 highlighted structural design, which are the front and rear wings and the flow of the car. The new F1 car has totally been given a new and much simpler front and rear wing that is meant to both generate consistent downforce when running closely behind another car and ensure that the front wheel weight is well controlled and directed down the car in the least disruptive way. Then there's the floor section. The 2022 F1 is bringing back a previously banned feature since 1982, which is a fully shaped underfloor tunnels, rather than the step floor used in the 2021 car. But you can't see it in this picture, but it's there. This will allow the teams to generate a large amount of efficient downforce through ground effect. To put some numbers on it, the research shows that the current F1 cars lose about 35% of their downforce when running 3 car lengths behind a leading car at approximately 20 meters. If the driver gets closer than that, about 10 meters, it will result in up to 47% of loss in downforce. The 2022 car, F1 and FIA, claims that the new design will reduce those figures to 4% at just 20 meters, rising to just 18% loss at 10 meters. Moving on to the methodology. What are the approach to this project? There are 2 parts in the methodology. The first one is a CAD modeling, and the second one is running the ANSYS simulation. So the software that we will use in this project is SolidWorks 2021, which will be used for the model development, and second one is the ANSYS Fluent 2021 for the purpose of simulation. So the next one is the flowchart of the project. We are going to go a little bit into detail about the processes. At the start of the process, we will first obtain and draw the most accurate and FIA-compliant model of the F1 cars. Then we will model and mesh the geometry in the ANSYS modeler. Afterwards, we determine what are the boundary and fluid conditions. Then we have to check for data validation if the numbers are logic compared to the previous studies and our expectations. If yes, then we have to decide if it's indeed a satisfactory result or do we need to modify the case study. If no, then we need to repeat the process and determine a different boundary condition. But once we obtain a satisfactory result, we shall plot a graph and then analyze the data according to the objective of the study. The design of a full-scale CAD geometry used in the study are the FIA F1 2022 and the Red Bull 2021 RB16B. The 2022 model is obtained from Sketchfab in a Blender format, which then imported into SolidWorks, while the 2021 design is drawn together with an anonymous contributor. These are adapted drawings designed in accordance with the FIA regulations. Therefore, it does not guarantee 100% accuracy with the actual models. The measurements, however, follows real-life models with the length, height, and width of the cars are roughly 5.4 meter, 0.96 meter, and 2 meter respectively. Next, the completed car models will then be exported into ANSYS as IGES file, and the next task is to mesh the design. The ANSYS meshing application produces a mesh to generate a computational mesh throughout the full volume. A 3-dimensional hexahedral mesh will then be generated. The image on the right depicts what it will look like after the mesh is complete. So the next step is to conduct the CFD simulation. But first, why CFD? While most large F1 teams have wind tunnels to experiment with, CFD simulations offer an excellent alternative to that, allowing teams to reduce the experimentation and associated costs, while accurately tuning the parameters using computational models. ANSYS Fluent is utilized in the study because aerodynamic field and air analysis is similar to fluid analysis. Now if you take a look at the table on the right, which are the boundary conditions, free stream velocity is set at 50 meters per second, pressure outlet is set to atmospheric pressure, fluid density is 1.225 kg per meter cubed, turbulent intensity is at 0.15%, and key epsilon is selected as a turbulent model. The Reynolds number is 12 times 10 to the power of negative 6, and the car distances are set to 0.25, 0.5, and 1 length of the car. The sample of the expected results are shown on the left. And this is the references for the pictures and information used in this presentation slides. And that concludes my presentation. Thank you for listening to my FYP presentation. Have a great day and Assalamualaikum.